Assalamu alaikum, everyone. My name is Ghazi, and I am a third-year medical student. Um, just like before getting started, this lecture was supposed to be delivered on the 23rd of or 22nd of December, but I've decided to move this lecture to like a week earlier because you guys are having your final, inshallah, on the 25th, I think, of December, and you're gonna have calm with it and more, like few days between them. So that's why I've decided to record this lecture earlier and post it on YouTube so you guys have enough time to watch the recording. And I'm also the head of a PAL team with Khalid Al-Sha'ir. Please, if you guys have any suggestions regarding our PAL sessions, we've made a lot of PAL sessions this semester, and I hope you guys benefit from these PAL sessions. Please, if you have any suggestions, feel free to contact us either by email, by WhatsApp, or if you guys see us on campus. We are really more than happy to hear any suggestion from you. Okay, so yeah, let's get started. Inshallah, I'm going to responsible for giving assimilation of nutrients, and I did this on purpose because this lecture I had a hard time on, like in my first year. It was a bit complex to me, so that's why I've decided to explain this lecture. I want to refresh my information regarding this lecture, and hopefully you guys benefit from it. Now, here are my contact informations. If you have any questions regarding this lecture, please feel free to contact me. Okay, so let's get started. So these are the objectives, and I will start by, like, let's before this, let's break the what's it called, the name of the lecture. So it's assimilation, which basically what will happen to the nutrients when they enter the intestines. Nutrients, I mean here, they are either proteins or carbohydrates or lipids. So we want to see how are these nutrients are processed in our body, how they are absorbed, what are the enzymes that act on these nutrients, the transporters. So obviously we'll have a lot of enzymes and transporters in this lecture, but I'll try as much as I can to simplify it, to simplify this lecture, inshallah. And again, if you guys feel that you didn't understand any concept, please ask me, okay? Now, starting with the first slide, here is, they're explaining basically the intestinal mucosa. Now, all of the processes, the absorption, are mainly is happening in the intestine, okay? Here's the intestinal mucosa, where in the intestine, as you guys know from your histology lecture, the small intestine is composed of the villi, okay, and the crypts, okay? So villi or villus and crypts. Now, the crypt is basically composed of the stem cells, and stem cells simply means that they are these baby cells that differentiate into a lot of cells, such as goblet cells, for example, enteroendocrine cells, and absorptive enterocytes or enterocytes in this context, which in the small intestine. So crypts, which are present in the stem cells, which are present in the crypts, are very important for the differentiation or the proliferation process in the intestine. And the differentiation mainly happens in like an upward manner. It happens towards the villus, like this, okay? So whenever stem cells is differentiating, it's differentiating or proliferating to this side, upward, and it will differentiate, as I said, into the absorptive or enterocytes that absorb the major absorptive cell in the intestine, or to the goblet cells or enteroendocrine cells. And as you guys remember that enteroendocrine cells, you've heard this cell before in the, I think, in the stomach, where enteroendocrine cells, such as, I think, enterochromaffin cells, enterochromaffin-like cells, are very important in that in the stomach in releasing like histamine and serotonin, I believe. But compared to the intestine, the stomach, like the enteroendocrine cells in the stomach are more, have a major contribute more to the action in the stomach compared to those in the intestines. The intestines, what our main focus is, the mature enterocytes in terms of absorption. Okay, now, so I mentioned that this stem cells are proliferating upward, and this is termed as epithelial turnover, where whenever the enterocytes, the stem cells are proliferating and differentiating, the cells that are present over here, like let's think about it like this. The cells, whenever the stem cells are proliferating, the enterocyte or the cells that are present over here, they are like going out, or they are desquamated to the lumen of the intestine. Okay, so that's the amount of, or exfoliation. Exfoliation means it goes out of the intestine to the lumen, and it will be shed by different mechanisms, such as as you guys know, the MMC, for example. Okay, so and this is termed as epithelial turnover. The amount of exfoliation that's happening over here is equals to the amount of the proliferation that happens over here. So equal proliferation to the exfoliation. That's why, and that's the basic homeostasis that's happening over here. Okay, I hope that makes sense. So that's regarding the first slide. This table is very, very, very important. I'm going to rely on this table for the rest of this lecture. The table represents, these are the nutrients, proteins, carbohydrates, lipids. Those nutrients, how are these nutrients absorbed in the intestine? So what enzymes, where are the enzymes that act on those nutrients? Okay, so for example, for the proteins, it has three, like the lumen. Okay, the lumen of the intestine. That suppose that this is the intestine over here. Okay, the lumen of the intestine. This is the microvilli, and this is the cell itself. Okay, the intracellular. The cell itself. Okay, so the nutrients, for example, carbohydrates, once it comes to the, or proteins, once it comes to the intestine, it will be, there are enzymes that are present in the lumen that act on proteins. Okay, and in the microvilli here, in the brush border, I will explain what a brush border in a bit, and inside, intracellularly, on inside the cytoplasm. Okay, while for carbohydrates, there are any modification. There's any modification process that happens inside the cell. While for lipids, only the lumen, there are only enzymes present in the lumen. You guys will understand this with explaining the upcoming slides. Okay, now we'll start with carbohydrates. Carbohydrates are very important, and whenever we are ingesting carbohydrates, we are ingesting it in the carbohydrates in a complex, I say complex, they are complex glucose polymers. Okay, and for carbohydrates, what are the enzymes that act on carbohydrates whenever we ingest them? We have the pancreatic alpha amylase, which is secreted by the pancreas in the duodenum, and we have the brush border enzymes, or the saccharidases. I will explain this more in the upcoming slides. Okay, now, whenever we are ingesting the carbohydrates, I said they are glucose polymers or starch. Okay, I can say that they are starch. And for starch are mainly the storage form of the glucose. Okay, so starch is composed of a lot of glucose subunits. So they are polysaccharides. Okay, they are polysaccharides. And polysaccharides simply means that they have more than, I think, they have a lot of, I don't know what's the exact number, but they have a lot of glucose subunits. Because we have polysaccharides, we have oligosaccharides, we have disaccharides, which is basically 2 glucose subunits, or monosaccharide, which is only 1 glucose. Okay, polysaccharides means there are a lot of glucose. in starch, and it is the storage form of glucose. Okay. Now, two types of starch. Whenever we eat, there are two types of starch: either unbranched, okay, unbranched starch, or they are the amylose, which have straight chain of saccharides, or the amylopectin, which is a branched polymer or branched saccharides. Okay, so for starch, two types: either amylose or amylopectin. Now, suppose that this is a glucose subunit, glucose, and those glucose are linked to each other by alpha 1,4 glycosidic linkage. Just memorize this, guys. Okay. So they are. Dr. Peter will not ask you what is an alpha glycosidic linkage, because I think you guys take it or took it in mole 1, or you might take it in mole 2. Okay. So amylose is those glucose subunits are linked by an alpha 1,4 glycosidic linkage. That's for amylose, and amylose is a straight chain polysaccharide. Now, amylopectin, which is a branch polymer, has a straight chain. Okay, has a straight chain which is linked by an alpha 1,4 glycosidic linkage. So this one here. Okay, it's an alpha 1,4 glycosidic linkage, and it is linked like vertically here. Okay, it's linked vertically here by alpha 1,6 glycosidic linkage, as you guys can see here. So it's linked by alpha 1,6 vertically, and horizontally by the straight chain. Okay, it is linked by an alpha 1,4 glycosidic linkage. Okay, great. I think this is easy. Okay, now moving. Okay, back to the pointer. Remember that our body, or the enzymes in our body, will only act on the alpha glycosidic linkage. They will not act on any form of beta 1,4 glycosidic linkage. And as this is the case of cellulose. So whenever we ingest any type, like any form of cellulose which has a beta 1,4 glycosidic linkage, our enzymes in the intestines will not act or will not hydrolyze this beta 1,4 glycosidic linkage, because the function of the enzymes, whether they are in the as I mentioned here, in the brush border or in the intestine, the lumen itself. Okay, the job of the enzymes is to act on the linkage. Okay, and they will act only on alpha linkers. I hope that makes sense. Okay, so yeah, so I think that's basically for this slide. Again, amylose, amylopectin, which is from the starch, and a lot of glucose subunits that are linked by alpha 1,4 or alpha 1,6 in the context of branched polymer. Yeah, and I talked about cellulose, and they are not hydrolyzed by amylases. Okay, so that again, this is an illustration, which is amylose, a straight chain. Okay, amylopectin, it's a branched polymer with like which it has a horizontal branch over here, and a straight chain by alpha 1,4, as I mentioned, and the branched, it is linked to the straight chain by alpha 1,6 linkage. Now, okay, so whenever we ingest the, for example, rice or potato or whatever, we ingest what's it called, a polysaccharide, okay, which is the starch. The starch will be hydrolyzed. It either has a alpha 1,4 glycosidic, alpha 1,6 glycosidic linkage, and this starch will be hydrolyzed by either both of these, which is salivary alpha amylase and pancreatic alpha amylase. That's the first step, which is because the first area where the carbohydrate comes to is the lumen. So it will come to the lumen before coming to the brush border, and brush border simply means this is the brush border, which is the apex of the cell. Suppose that this is the lumen and this is the brush border. For carbohydrates, we have enzymes in the lumen and enzymes in the brush border. And both of these enzymes act on the hydrolysis of what's it called, carbohydrates. Okay, moving on. So we have salivary alpha amylase, which is secreted by the salivary glands in the mouth. Okay, by the salivary gland, we have the salivary alpha amylase, and we have the pancreatic alpha amylase. Here it's written that, and the notes in the notes of Dr. Peter, it's written that salivary alpha amylase only contribute to 5% of the hydrolysis or the digestion, hydrolysis of the carbohydrates. However, 95% is done by the pancreatic alpha amylase. Okay, so here's the carbohydrate. And here's the salivary alpha amylase, which is upward. Okay, and suppose or assume that here's the what's it called, the pancreas by the action of cholecystokinin. As you guys know from the pancreatic secretion lecture, cholecystokinin will be released because there's a presence of the carbohydrates. So once cholecystokinin is released, it will activate the pancreas to secrete its contents, whether it's pancreatic alpha amylase or other proteases in the context of proteins, but we are talking about carbohydrates now. So the pancreatic pancreatic alpha amylases are released from the pancreas over here to the going to the ampulla of Vater, to the sphincter of Oddi, to present in the duodenum where the carbohydrates coming. So here's the carbohydrate, here's the pancreatic alpha amylase, which comes from the pancreas. Now, in the duodenum, in the proximal part of the duodenum, the pancreatic alpha amylase will work on the two types of starch. As I mentioned, guys, I mentioned that starch will be in the body in the form either amylose, which is alpha-1,4 linkage, or amylopectin, which has an alpha-1,6 linkage. Okay. Now, and it will act on the amylose or amylopectin, and will cleave the alpha-1,4 glycosidic linkage, only alpha-1,4. So pancreatic alpha amylase is responsible only for degrading or cleaving alpha-1,4, not alpha-1,6. Okay, so in amylose, again, before continuing, for alpha amylase, it's an endoenzyme. It means that it cleaves only the internal peptide. Internal peptide or interior peptide, which is the peptide that's not present in the terminal end of the chain. Okay, it's in the middle of the or the anterior part of the chain. So what's it called, as the pancreatic alpha amylase will come to amylose and will cleave the internal part of the straight chain over here, yielding two important byproducts, which is either maltotriose or maltose. So maltotriose or maltose, and this happens because of the alpha amylase. We are here. Remember that we are in the lumen. Okay. Now maltose. What is the difference between these two? Is that maltose simply a trisaccharide which has 3 glucose subunits, and this is for maltotriose, and maltose is a disaccharide which has 2 glucose subunits. Okay, so trisaccharide, triose, 3 trisaccharide, and maltose, disaccharide, which contains 2 glucose subunits. Okay, so that's for amylose. I said that it only cleaves the alpha-1,4 linkage. But what about amylopectin? For amylopectin, it only again will cleave alpha-1,4 linkage. Okay, so this is a chain, this is another chain. They are linked with this chain. Subunits in this chain are linked by alpha-1,4, and again this chain by alpha-1,4. They are linking with each other by alpha-1,6. For alpha amylase, pancreatic alpha amylase, it will act on each chain individually, yielding maltose and maltotriose, again maltose and maltotriose. But if there is like still the alpha-1,6 linkage present, the byproduct is named as alpha limit dextrin. So alpha limit dextrin mainly obviously means that there's an alpha-1,6 linkage in the byproduct. Here there's no alpha-1,6 and there's no alpha-1,6, only alpha-1,4 glycosidic linkage. And remember that by pancreatic alpha amylase, glucose, which is a monosaccharide, is not a product. Glucose is not a product. The products are either disaccharides or trisaccharides. Okay. I hope that makes sense, and that's it for that slide. Let's summarize it quickly. Amylose, amylopectin, amylose by alpha amylase, maltotriose, and maltose, which the pancreatic alpha amylase is an endoenzyme. It's not like an exo enzyme. Okay, endoenzyme simply means an internal peptide. It cleaves the internal, not peptide, sorry, internal link. Okay, glycosidic link, I mean. And that's the case of the which happens in the amylose, happens in the amylopectin. But in amylose, it's only alpha-1,4 linkage. In amylopectin, we have a byproduct that's having alpha-1,6 glycosidic linkage, which is called alpha-limit dextrin. Okay, now moving into the brush border. I brought this image to explain what a brush border is. A brush border means, again, it's the apex of the cell. This is an enterocyte. Okay, the apex of the enterocyte has microvilli, and this microvilli, there's the presence of the brush border enzymes. Type, what brush border enzymes do we have? Maltase glucoamylase, sucrase isomaltase, and lactase. Okay, guys, try to repeat it as much as you can to like memorize this enzymes, because they are very important to keep in mind. What I remember from what's it called, this lecture, Assimilation of Nutrients, that you will definitely will have an MCQ asking, sorry, an SAQ asking about one of those enzymes. Okay, either the brush border enzymes or the enzymes that are the luminal, or the proteases and the proteins or lipids as well. So please try to memorize this lecture well. And it's not hard. Wallah, it's not hard. It's like, take it as a story. Okay. Now, we talked about here the lumen. Now talking about a brush border. For brush border, we have enzymes present over here, which are those enzymes. Where? Oh, sorry, those enzymes. Okay. So those enzymes are present over here. Now, okay, so maltose, for example, here, or let's start with alpha-limit dextrin. For alpha-limit dextrin, it will go from the lumen over here, comes here to the brush border enzymes such as sucrase, isomaltase in case of alpha-limit dextrin. So alpha-limit dextrin will go to sucrase isomaltase. Sucrase isomaltase will cleave the alpha-1,6 linkage, yielding maltose and maltotriose. Okay, because we are cutting this link over here. We're cutting this link. Okay, so our byproducts are maltose. Okay, maltose. Okay, and maltotriose. These are our byproducts. I think it's easy, right? Now, so this is okay. So this is maltose, maltotriose. Maltose, maltotriose will be further cleaved by the action of the enzyme maltase glucoamylase. Okay, so by maltase glucoamylase, remember maltase, okay, maltase glucoamylase will cleave maltose and maltotriose, okay, to glucose, okay, to glucose, which is the monosaccharide, because if you guys see here, I don't know where exactly. Yeah. So carbohydrates are only absorbed as monosaccharides. And what monosaccharides do we have? It's either glucose, sucrose, I think glucose, fructose, or galactose. These three are the monosaccharides. We'll discuss it later, or we'll discuss it in a bit, I think, in this slide. Okay. So so maltase glucoamylase will cleave maltose and maltotriose to glucose. Easy, easy. Okay, and I've talked about alpha-limit dextrin, where the byproducts are maltose, maltotriose, which will go again and will be further cleaved by maltase glucoamylase to yield glucose. Okay, now what about the disaccharides, which we take, for example, sucrose or lactose in the milk? for the in this enzyme. Sucrose will be cleaved by sucrase isomaltase. Okay, so sucrose is a disaccharide, will be cleaved by sucrase isomaltase to yield glucose and fructose. So glucose and fructose by sucrose, and this is happening again by this enzyme here, which is responsible for alpha-limit-dextrin, and it is responsible for cleaving sucrose. So sucrose will give glucose and fructose in this picture, and lactose by lactase, again, sucrose, sucrase, lactose, lactase, maltose, maltotriose, maltase. So the enzymes are like correlate to the name of the enzymes, highly correlate to the name of the saccharides. Okay, so again, lactose by lactase, it will yield glucose and galactose. Okay, so memorize this. Lactose will give glucose and galactose, while sucrose will give fructose and glucose, which all of these are monosaccharides, which we want them to in order to absorb them in the intestines. I hope that makes sense. Okay, I hope that makes sense, and I think that I explained everything in this slide. Okay, I will summarize what's happening in the carbohydrates once I finish carbohydrate part. Okay, now these are the transporters. This is very important, and you are familiar with like the concept of transport and the electrochemical gradient and so on from your previous lectures in GI. Starting with the what drive the electrochemical gradient here, what is the trigger is the sodium potassium ATPase, where sodium is pumped out of the cell, potassium is going into the cell. Now we have less sodium inside the cell here, less sodium. Okay, so and as there is less sodium inside the cell, as there is less sodium inside the cell, we want the sodium to enter the cell. So that's what drives the glucose and galactose to enter. So decrease in sodium here because of the electrochemical gradient made by sodium potassium ATPase. Sodium 2 like particles of sodium will enter the cell, and this will happen with glucose and galactose. Okay, this sodium will enter with glucose and galactose. So that's how glucose is absorbed into the enterocytes. So glucose or galactose, very important. Glucose or galactose will enter the enterocytes because of the electrochemical gradient that happens due to sodium potassium ATPase. They will enter. They will enter like by the transporter, which is called SGLT. SGLT. Remember, S sodium GL glucose transporter. Easy. Sodium glucose transporter will enter the cell. And that's how basically how our glucose and galactose are absorbed into the cell. Okay, what about the fructose? Fructose has a different transporter. It's not like the sodium or it's not like the glucose or galactose. Fructose has a different transporter. And what is the transporter for fructose? That transporter is called GLUT5. GLUT5. Okay, so that's for fructose. And it is, as in here, it is not coupled to sodium absorption. It will enter by itself without any electrochemical gradient or so on. Okay. Now, this is important here. Fructose will enter by GLUT5. Besides, again, fructose will enter by GLUT5, but the glucose or galactose that enters here by SGLT1 plus the fructose will exit to the blood. Here's the blood, the basolateral membrane. Here's the blood, the portal vein. Okay, the portal vein. I will explain what a portal vein and where does it go. And you guys, I think you are familiar with it. So, glucose and or galactose or fructose will diffuse to the basolateral membrane by GLUT2. Okay, by GLUT2. So enter by GLUT5 for fructose. Remember, what I from like in year 1, I remembered this by that. Remember that this is a 5, okay, and this is fructose. Okay, so they are the same. So fructose will enter by somehow the same, I think. Okay, so fructose will enter by GLUT5 and the whole three monosaccharides will exit by GLUT2 to the basolateral membrane. And that's basically how this happens. Okay, now this is important. I don't know if it's important or not, but you guys, I've spent in year one, I've spent a lot of time to understand this slide, but it was really like complex. I will try to simplify it as much as I can. Look, column simply means the large intestine. Okay, monosaccharides, if they are not absorbed in the small intestine, they will not be absorbed in the large intestine. There is no mechanism to absorb monosaccharides in the large intestine. So the only way that monosaccharides to be absorbed is the small intestine. Okay. Now, for the monosaccharides, they cannot be absorbed as in here by the column, because there are no transporters in the large intestine for monosaccharide to be absorbed. Because let's explain the graph. This graph. So this graph simply represent, in the y-axis, here is the organisms, or here are the organisms. Organisms simply means the bacteria. Okay, and the x-axis we have the different parts of the GI, of the gut. Okay, stomach, duodenum, jejunum, ileum, and large bowel, or the large intestine. So as you guys know, in the stomach the pH is only 2. In the duodenum there is the secretion of the different proteases, amylases, lipases, and so on. So there are a lot of enzymes, and there is bile salts. There are bile salts that are released by the what's it called, the pancreas, the bile. Yeah, and there is the MMC. Okay, there is the MMC. So okay, so again, this is what happens in the stomach, where we have like the pH is low in the stomach. In the duodenum, we have a lot of enzymes, and we have this propulsive motility MMC, which is this protective mechanism. I think you guys are familiar with it, which happens, I think, every 90 minutes. Wallahi, I forgot, to be honest, but it's not mentioned in this lecture. No, it is like a protective mechanism which will move any residual material present either in the stomach or in for example, the intestines and so on. Okay. This decrease in acidity, enzymes, MMC, are not present in the large bowel, in the large intestine. This is very important. They are not present in the large intestine. So that's why it is like a typical area for the bacteria to live. Okay, so the bacteria, we have a lot of bacteria present in the large intestine. Okay, a question: why, like, don't bacteria live in the stomach or in the small intestine? This is simply because in the small intestine, in the stomach, we have a lot of toxic, like toxic materials or so on, enzymes. They are toxic to the bacteria. Okay, so the bacteria will be killed easily in the stomach or in the small intestine. However, in the large intestine, since we don't have these protective mechanisms, that's why the bacteria will live there. But the bacteria that are present in the large intestine, they are not, they don't have any, they don't harm us. Okay, they don't harm us in normal conditions. So normally bacteria live in the large intestine. Okay. I want you guys to understand this very well. So as you guys see, the bacteria is present in the will present in the large intestine in in high amounts, and that's why, because of what I've discussed. And it's written here that the bacteria, because there are a lot of bacteria in the microbiota, or the normal flora, the normal epithelium of the what's it called, of the intestines, because there is a lot of bacteria. It contributes to 40 to 60% of the stool. Okay, so 40 to 60% are composed of bacteria. So whenever a clinician takes any sample from the stool, and he examined it. He will find a lot of like bacteria present, which is these bacteria are the normal microbiota of the large intestine. Okay, so that's what they simply wanted to want you guys to know from this slide. Okay. Okay. Now, see this, guys? Large intestine. This is the bigger picture of the large intestine. These are the colonocytes. The colonocytes that are present in the large intestine. Colonocytes are the cells that are in the large intestines. In the small intestine, we have enterocytes. Large intestine, we have colonocytes. Now, for colonocytes, they like in the normal microbiota of the large intestine, it harbors bacteria. And whenever there is any, for example, undigested carbohydrate by the small intestine, for example, cellulose, in this context for carbohydrates, cellulose, or in the context of lipids, bile salts, or any undigestible lipid material, for example. We'll discuss it in the lipid part, don't worry, guys, okay? Or proteins, any desquamation of the cells, as I mentioned over here, if you remember, that cells are desquamated here, which is the normal homeostasis in our body. These cells will be shed by the MMC and will reach what's it called, reach the large intestine over here. So they will reach the large intestine. Okay, let's again talk about carbohydrates and focus on carbohydrates. Okay, in the large intestine, once carbohydrates, the undigested carbohydrates reach the large intestine, they will be fermented by the action of bacteria that are present over here. So this is the bacteria that are present. Bacteria maintain or get its energy from where? From the what's it called? From the carbohydrates that are undigested. So bacteria will take their energy by the fermentation process over here. After fermenting, as you guys know, the fermentation, what are the products? We have gas plus acid, right? So carbohydrates, whenever it is fermented, it will yield short chain fatty acids plus gas. So short chain fatty acids plus gas. This short chain fatty acids will be absorbed by the colonocytes, and as it absorbed by colonocytes, it will provide the energy for the colonocyte. Okay, so the energy for bacteria by the fermentation process, easy. What about colonocytes? They will take short chain fatty acids, and as they take short chain fatty acids, they will take their energy from them. Okay, those are short chain fatty acids, basically acetate, butyrate, or propionate. And fatty acids will enter colonocytes by the action of this transporter. We have another transporter which is coupled to sodium, which is sodium short chain fatty acid. What transporters do we discuss so far? We have SGLT1, which is sodium, again, sodium with glucose or galactose, and GLUT5 and GLUT2. Again, so sodium comes here with another transporter. It is co-transported with short chain fatty acids. So glucose or galactose plus short chain fatty acids are coupled to sodium. Okay, so these short chain fatty acids will provide energy for the colonocytes, where 90% of short chain fatty acids will provide energy. Less than 5% are not absorbed. They will be excreted in feces. They continue their pathway in the large intestine, and 5 or less than 5% will go to the blood. Will be here, diffused to the basolateral membrane to the blood, and by the portal vein to the liver. Okay, the portal vein which is present over here. Yeah. So that's it, I think, for this slide. Yeah, so we have over here short chain fatty acids, which either feces, portal vein, or energy for the colonocytes, and bacteria, which will take their energy the normal bacteria present in the large intestine takes their energy from the fermentation process, and the gas, which is the other byproduct besides short chain fatty acids, will be expelled as either CO2, H2, or flatus. Okay, and yeah, I think that's it for this slide. Okay, this is important. These two slides are very important, which is lactase deficiency and sucrase isomaltase deficiency. This is very important. Now, for lactase deficiency, suppose that an individual is having a lactase deficient. He's a lactase deficient, or he is a lactose intolerant. It means that lactose is not broken down to its monosaccharides, which is galactose plus glucose. This means that lactose, or the monosaccharides, this means that because there is no monosaccharides, the lactose will not be absorbed. Am I right? So lactose will not be absorbed because it's not a monosaccharide and it's not broken down. So lactose will accumulate where? It will accumulate and build up in the small intestine over here, or down the large intestine, or so on. Okay, so large intestine or small intestine. As lactose reaches the large intestine, it will be fermented by the bacteria. Okay, and as it fermented by bacteria, it will either yield the gas, which is CO2, CH3, and H2, or short chain fatty acids. Okay, we'll discuss this in a bit, but let's talk about the building up of lactose. When lactose build up here, it means that we have a lot of concentration where? In the small intestine. Am I right? So there is a lot of concentration over here. It means that because of the osmotic gradient, water will go from the blood where? To the lumen, right? So because there are a lot of solutes over here, blood will go from the fluid will go from the blood, or the blood will go from here to the lumen. This will bring about there will be a lot of fluid in the intestine, and that what will lead to the diarrhea that is experienced by patient with lactase deficiency. Let's repeat this again. Lactase deficiency, it means that lactose is not broken down. And as it's not broken down, it means that glucose and galactose is not there. So lactose is not absorbed because it's not a monosaccharide. It's a disaccharide, right? Lactose will build up over here. And as it builds up here, because of the osmotic gradient over here, the increase in solutes over here, the blood will escape from its side to the lumen. So there will be a lot of fluid in the lumen. And as there is a lot of fluid, this will promote to the diarrhea that are experienced or felt by patients with who are lactase deficient. Okay, I think that's easy, right? This is very important, guys, to understand. Please, if you didn't understand this, let me know. Okay, what about large intestine? In the large intestine, lactose will be fermented by bacteria into CO2, CH3, and H2, and yeah, and we have here the short chain fatty acids, where are as in here, yeah, the short chain fatty acids which will continue its pathway in the colonocytes and so on. Type. For H2 over here, we have it's very important as it's clinically significant. How is it clinically significant? How do we check that the patient is having is a lactase deficient? We inject or we give a patient lactose, and we will measure two things: either H2 in breath in expiration, or we'll take a sample from his blood to see the glucose, measure his glucose levels. Okay, so either glucose or H2. Okay. Now, For H2, so as we let's like follow this graph. As we ingest lactose to a patient, if he is lactase deficient, it means that there are bacteria that's fermenting this lactose to yield H2, and after, if we measure his H2 when he's expiring, after about like 2 hours, for example, we'll see that there's a significant increase in H2 in the breath. Okay, and this is very important as this patient is a lactase deficient, and it's like a diagnostic for lactase deficiency. Lactase deficiency. Now, for what about the blood? Again, if we give a patient, if we give any patient lactose, okay, we're gonna see that the glucose will not increase in the blood. Okay, so this is the graph again. This is the glucose levels, and we are seeing the glucose in the blood. If we give a patient lactose, and if he is lactase deficient, it means that the glucose will not rise. So it will be baseline in this patient. Okay, as in here. But however, if the patient is not lactase deficient and we give him lactose, the glucose will increase in the blood. The glucose will increase because he has lactase, the monosaccharides are being produced and they are transported to the blood. I hope that makes sense, and that's for the H2 breath test. So H2 or glucose, H2 or glucose. Okay, what about sucrase? What about sucrase isomaltase deficiency? It's the same concept, guys. As you remember over here, that sucrase isomaltase is important because it will cleave sucrose into two. If we again cleave sucrose in sucrase isomaltase deficiency, there is no sucrase isomaltase. It means that sucrose is not cleaved into glucose and fructose. So it means that sucrose will build up in the sucrose will build up in the intestine, leading to this diarrhea and so on, the same as lactose over here. So again, how do we diagnose this? We diagnose this by measuring the H2 breath, making the H2 breath test as and by injecting. Of course, here we're injecting the patient lactose, and here sucrose. Okay. I think that's it. Yeah, I think that's it for now. Again, we have one important thing here. I don't know if this is important or not, but they say that if there's any patient who is experiencing constipation and we want to promote diarrhea, we give them what? We give them dietary cellulose. So cellulose will not be absorbed, and as cellulose is not absorbed, it will accumulate over here, and as it accumulates, there will be the water will follow, and there will be diarrhea. It will oppose the effect of the constipation. Okay, so I don't know if this is important or not, but from what I know, that this is not really important. But at least you guys understand the concept behind this. So again, if the patient is experiencing diarrhea, we give them cellulose, and as we give them cellulose, it will build up over here. As cellulose is not absorbed, as I guys mentioned, because it has a beta 1,4-glycosidic linkage. So as cellulose is not absorbed, it will accumulate over here, and the accumulation of cellulose will bring about the diarrhea experience in will bring about the opposite mechanism of the constipation or preventing constipation in such patients. And that's it for carbohydrates. Let's move back to this table. Okay, so for carbohydrates, when we eat carbohydrates, it's in the form of starch, and starch is either amylopectin or amylose. And for starch to be broken down, or for carbohydrates generally to be broken down, it's either broken down by enzyme, the effect, or it's broken down by both of these or in both of these locations. What are those locations? In the lumen, this is the first one, and the second one in the microvilli. In the lumen, it's broken down by the effect of the amylases. Okay, the pancreatic amylase that's released by the as I said, the pancreatic amylase, which here in the lumen, it will break down the saccharides. Okay, and the other area is the brush border, which are the saccharidases present in the brush border. I don't know if I explained the saccharidases. Yeah. This is the saccharidases over here, which is either maltase glucoamylase, sucrase isomaltase, and lactase. Okay, so that's what happens in the what happens here in the brush border. Both those enzymes and the lumen, we have the pancreatic alpha amylase or the salivary amylase, but salivary amylase does not contribute as much as, for example, pancreatic alpha amylase, which is the major contributor to the hydrolysis of carbohydrates in the lumen. Okay. Yeah, and those are the transporters, how glucose and galactose transported by SGLT1 or by GLUT5 for fructose, and all of these by GLUT2 to the will go to the blood by GLUT2. And this is the fermentation with short chain. It happens in the large intestine, as I said, short chain fatty acids, which will provide the energy for the what's it called, the colonocytes. Fermentation of bacteria provide the energy for bacteria, and by the portal vein, it will go to the some of them by the portal vein will go to the liver. Some of them will be excreted in feces. That's for short chain fatty acids. For gases, it will be it's highly has a high significance, clinical significance in the context of lactase deficiency or sucrase isomaltase deficiency, where we measure H2 to know if this patient is lactase deficient or not, or sucrase deficient or not, or we measure glucose in the blood in the lactase deficient people. Okay, so I've discussed carbohydrates, then now moving into proteins. Now for proteins, okay, so for proteins, we have the hydrolysis happening in the lumen, in the microvilli, and in the enterocytes. So inside the cell, at the apical part of the cell, so inside the cell, at the apical part of the cell, and in the lumen. Okay, so as you guys know that proteins can be made like inside the body, which are called non-essential proteins or amino acids, and outside the body, which are the essential. Here's written that outside, like we took our proteins, 50% of our proteins are from outside the body, and 50% from the inside the body. Okay. What are the source of proteins? Like the dietary source outside the body, or the essential amino acids, meat, eggs, as you guys know, and so on. There's like a lot, like a prolonged list for the essential amino acids and the sources of essential amino acids. Now, what about the endogenous amino acids? They are made in the body, or they are coming from the enzymes that I've discussed, the proteases. We'll discuss, inshallah, in the upcoming few slides, or from the secretions of the cells and so on, or by shedding the epithelial cells. Moving back here, I said that there's exfoliation, there's shedding of the mucosal cells, or either because of this process, or some cells they are harmed by the gastric mucosa, for example, the gastric acidity. It will harm the gastric mucosa, so cells will be harmed. That's why it will be shed. And those cells contain, like most of them are, the most contributor of these cells, or composition of those cells, are proteins. Okay, so this is basically what an endogenous source is. Okay, now, so in the lumen, we have the pancreatic proteases, and such as pepsin, trypsin, so on. We'll discuss it. Brush border, we have the peptidases in the brush border, aminopeptidases, I think. And for the cytoplasmic, we have peptidases inside the cell. Moving on here. So as you guys know, the effect of CCK, whenever there's a chyme that robulus that has high protein content, high lipids, high carbohydrates, CCK will be released. And as CCK is released, it will stimulate the pancreatic, what's it called? Pancreatic, the enzymes to be released from the pancreas. Okay, I've discussed this a lot, and you guys should be familiar with this. Now, what are the locations for the hydrolysis, the luminal hydrolysis of proteins? So first of all, we have in the stomach. Okay, what do we have in the stomach? We have pepsin, which is released by the chief cells in the stomach, which will be released as proenzyme. Then it will be cleaved by the acidity and so on. Like, long story, you guys know it. It will be active and will what's it called? It will cleave proteins. As the salivary amylase, if you guys remember, salivary amylase is not the major contributor to the to hydrolysis of carbohydrates. Here is the same. Pepsin is not the major contributor to the hydrolysis of proteins, because pepsin, whenever pepsin is released, the what's it called? The once it reaches the duodenum, there is the pH in the duodenum is increased, as this graph indicates. So the pH in the duodenum is increased. So that's why pepsin will be inactivated by the alkaline environment of the duodenum. So that's why pepsin does not contribute fully to the hydrolysis of the proteins. Okay, besides pepsin, we have pancreatic proteases, trypsin, chymotrypsin, carboxypeptidases A and B, and elastase. Okay, they are activated they will be activated in the alkaline environment, and again, as the case of pepsin, those are proenzymes. Okay, proenzymes that should be activated. And how they are activated, I brought this slide from the pancreatic secretion lecture. So we have, for example, here trypsinogen, OGEN, means that this is a proenzyme which is not active. We should activate this to make its function. So trypsinogen, by the action of the brush border enteropeptidase in the enterocyte, it will be transformed into trypsin. And the trypsin will activate the other proteases, pancreatic proteases. So first of all, the first action is by enteropeptidase, and then the rest by this product, which is trypsin. The active trypsin will cleave chymotrypsinogen into chymotrypsin, proelastases into elastase, and blah, blah, blah. Okay, so that's it for the active. How do we activate, or how are the pancreatic enzymes activated, the proteases, the pancreatic proteases being active, or how to activate it? Okay, so this is important again. I don't know if it's important or not, but they mentioned it in the notes. They said that if there is any gastrectomy or stomach resection, it means that there is no pepsin. But they found out that after conducting a lot of researches and so on, that with gastrectomy, the protein assimilation is not affected at all. Okay, it's not affected because we have the pancreatic proteases over here. So the protein assimilation is not impaired when there is when they perform or if there is gastrectomy, or the patient or an individual do not have stomach. Okay. So yeah, so that's it for this slide, where we have again the proteases from the pancreas. This is from the chief cells. Activation by this, where you guys should know it. And I think Abdurrahman, he's the one who explained pancreatic secretion. He did explain it well, I'm sure. And yeah, okay. And I think you guys are familiar with this again. Here are the proteins by the pepsin, which is an endopeptidase. This is important. So those proteases are we have two types of proteases. Either in terms of cleavage, I mean, either endopeptidase or exopeptidase. Now, endopeptidase simply or obviously means that these enzymes will cleave the peptide linkage, which is in the middle, okay, or in the interior portion of the protein. So this is a protein, okay, in the interior portion of the protein where an endopeptidase will act. Chymotrypsin, or in this case, trypsin, chymotrypsin, or elastase, or pepsin. And what about the exopeptidase? Exopeptidase, EXO, external, it means in the terminal end of the protein. So EXO, external terminal end of the protein, as carboxypeptidases A and B, which is the only one, remember the long name here, it is the only one that's exopeptidase. For endopeptidase, the rest, which will act in the interior part of the protein, exopeptidase in the terminal, either in the N-terminal or in the C-terminal. The proteases, once they like do their functions, they will yield either di and tripeptides, oligopeptides, or amino acids. Okay, so di and tripeptides, amino acids, and as you guys know the story. Now, what is the next step? It's either to cleave di and tripeptides, or to cleave those peptides, or so on. So this will happen by the brush border enzymes. So brush border enzymes, which are either carboxypeptidases or aminopeptidases, okay, their major function is to remember those, okay. They will come here from the lumen after they are being cleaved, or after the process happens in the lumen, they will come here. They will be further cleaved by peptidases. So the oligopeptides will be cleaved into di and tripeptides. The di and tripeptides will be cleaved into amino acids, for example, and so on. Okay. If the product is amino acids, so those amino acids will enter the cell by sodium. What do we have so far for sodium? Sodium glucose transporter and sodium short chain fatty acid transporter. Okay, and here's the third one, which is amino acids sodium transporter. They will enter the cell by this transporter, which is presented at the brush border. That's for amino acids. What about what's it called, PEP1, or this transporter PEP1, which is responsible for di and tripeptides? We have here the code. It will be co-transported with a new one, which is H. Okay, and this H is fueled by the sodium hydrogen exchanger. So sodium hydrogen exchanger will maintain the electrochemical gradient for H. So H will be like recycled here, just to make sure that the di and tripeptides enter the enterocyte. Okay, so that's it for the brush border like enzymes and brush border transporters. We'll discuss it more here. Then now we have di and tripeptides enter the cell. We have amino acids as well in the cell. Now these so remember that oligopeptides cannot enter, oligosaccharides cannot enter, only monosaccharide enter in the context of carbohydrates. In the context of proteins, di and tripeptides can enter the cell, and amino acids. So di and tripeptides enter by PEP1, amino acids by this transporter exchanger, or sorry, symporter. Di and tripeptides by the action of cytosolic peptidases will yield amino acids, and we'll see what's the next story here. Yeah, so here they are remembering us of the SGLT1, which I've discussed a couple of slides earlier, and sodium amino acids again, and this is again happening because of this. This is the electrochemical gradient, which is the sodium potassium ATPase. Sodium will exit the cell. Sodium is now decreased in the cell, so we wanted the sodium to enter the cell, and the sodium will enter the cell, and will make sure that amino acids will enter with it. So sodium and amino acids will enter the cell, and there is and they will exit the cell in a. Here we'll discuss it here. Okay, wait. So yeah, here they are saying that this co-transporter, which is sodium, what's it called, sodium amino acid co-transporter, has a broad specificity. It is not like selective to what's it called? For example, a single amino acid. No, it has a broad specificity where a lot of amino acids can enter from this co-transporter. Okay, and here they are saying that nutritional deficiencies are rare, so no deficiency in this transporter. And if there is any deficiency happen, this will lead to cystinuria, cystinuria, which basically proteins will build up in the kidney and so on, or in urine, and this will lead to kidney stones. This you guys will discuss or will understand this more in the renal block in the second semester, inshallah. Okay, so for peptide transport, we have here I said this is the major electrochemical gradient, the driving force, where sodium will be out. Now, sodium will enter by this exchanger. This will allow the amino acids, the peptides to enter, as in here. Okay, so this will allow the peptide to enter because of the driving force happened by the ATPase. Sodium will enter, hydrogen will be recycled here, and the di and tripeptides will enter. And as di and tripeptides enter, we have peptidases or proteases, as you guys remember here. So we have proteases or peptidases over here, and these peptidases will break down those di and tripeptides into amino acids. Single amino acids will exit the cell. I don't know, they are not specifying a transporter over here. But yeah, that's the major mechanism behind the absorption of the either amino acids or di and tripeptides. And remember that di and tripeptides can exit the cell in their form without being broken down, but this happens in only less than 10%. And I've mentioned here that this is the portal vein, so they are all going to the portal vein to be to go to the blood and distribute in our body. Okay, for this slide, I don't know why they are bringing this slide to you guys, because this is a bit advanced. They are talking about peptidomimetics. Now, what are peptidomimetics? From its name, it means that those substances that are similar or mimics peptides. What substances mimic peptides? We have, for example, beta-lactams, which is a group of class of drugs. ACE inhibitors, it's another class of drugs you guys will take, inshallah, in second and third year. They mimic whenever we take a drug. Okay, this drug will go to the again to the duodenum, and from the duodenum, from the enterocytes, will enter the same transporter here, the PEPT1 transporter. Okay, so it will enter in the PEPT1 transporter, then it will exit to the portal system, and then will distribute in the body as the case of other proteins. Okay, so that's basically how the drugs works in our body. So I think that's what they want you guys to know, but I don't think they don't expect any question from this slide. Just understand the basic concept behind what peptidomimetics are. Okay, so that's it for proteins. Let's summarize it quickly. So we have for proteins in the lumen, microvilli, and enterocytes. In the lumen, we have either pepsin, which is by the stomach, or but pepsin does not contribute to does not have a major contribution to the absorption or to the hydrolysis, of proteins. So it's the effect of other proteases that act on the proteins, which are the proteases that are released from the pancreas. So that's from the lumen. So it will, as in here, yeah. So it will those proteases will be active by this. Okay, enteropeptidase trypsin will activate other proteases, and those proteases will act on the proteins either in an endopeptidase manner or an exopeptidase manner, yielding di and tripeptides oligopeptides or amino acids. And those, for example, dipeptides will come to the brush border enzymes. Brush border enzymes such as aminopeptidases or carboxypeptidases, the brush border will break it down or further. If it's an oligopeptide, we'll break it to di and tripeptide. If it is a dipeptide, we'll break it to amino acids. Okay. Now, if it's an amino acid, it will enter the cell co-transported with sodium. If it's a di or tripeptide, it will enter the cell co-transported with hydrogen. Yeah. So okay. Co-transported with hydrogen. What is the major driving force? Is the electrochemical gradient established by sodium potassium ATPase. Once inside the cell, the di and tripeptides will be further like broken down into amino acids, and that basically happens by peptidases. Peptidases will have amino acids, and amino acids will exit into the portal system and get distributed in our body. So that's it basically for proteins. Moving into lipids, which is the most complicated part. Please, guys, try to bear with me. Inshallah, I will try to make it easy. And for lipids, it requires, first of all, pancreas. It is only in the lumen. There is no brush border. There are no brush border enzymes, no intracellular enzymes to digest or hydrolyze lipids. So lipids, it happens for the hydrolysis of lipids happens in the lumen by the pancreatic enzymes or the plus bile acids or bile salts. We'll discuss this. So yeah, so for lipids to enter the body, lipids will enter, as you guys know, as triglycerides. Okay, and triglycerides basically it is 3 fatty acids, okay, and 1 glycerol. So 3 fatty acids and 1 glycerol. So that's what triglyceride is. And most of our diet, if we are consuming like diet, what's it called, rich, for example, that fat-rich meal, it's mostly composed of long-chain triglycerides. Okay, so long-chain triglycerides simply means that it has more than 12 carbons. Okay, what about medium chain? Medium chain, they have less than 12 carbons. So we might like the diet might will have long chain, medium chain, short chain fatty acids. So different morphologies of triglycerides or lipids. Okay, now these are the what dietary lipids. Then gastric lipase. So gastric lipase is simply those enzymes, okay, that are released by the stomach. They are released from the chief cells. Okay, they are released from the chief cells. What other like enzyme is released from chief cell? It is pepsin. Yeah, so pepsin is released from chief cells. So we have again gastric lipases. Gastric lipases act on the pH of the stomach, which is like slightly lower pH, which is from 4 to 5. Yeah, and it acts. It's written here. It acts target mainly medium chain triglycerides. I don't know if this is important or not, to be honest, but it is not correlated, does not have any correlation with bile salts or any cofactor. We'll discuss this later and we'll emphasize on this point. And why, again, lipases, gastric lipases, does not contribute to the main action of the hydrolysis of lipids, simply because that when it reaches the intestines, there's this alkaline environment, and there's a trypsin that will cleave gastric lipases, as the same concept which we saw here for pepsin. So yeah, pepsin, because once it reaches the stomach, once it reaches the duodenum, there is increase in the pH, which will not allow the pepsin to do its function. Okay, what's the major contributor again? Our star is pancreatic lipase. So pancreatic lipase contribute to 80 to 90% of the triglycerol hydrolysis, and it highly depends for the pancreatic lipase to act. It highly depends on bile salts and co-lipase. We'll see what are bile salts and co-lipase in a bit. Okay, and we have again these bile salts, phospholipids, and which facilitate the absorption, okay, of triglycerides by has two important jobs, which is emulsification and solubilization. So emulsification and solubilization, Kaman will see it in a bit. Yeah. Okay, so here is an important here's an important point. There's a star over here. They said that in the notes, it's mentioned that if an individual or if a newborn, in a newborn, is like the pancreas is not mature, so it will not like release the mature pancreatic lipase. Okay, so gastric lipase will act in that at that time. So gastric lipase will be the major contributor in newborns, okay, because their pancreas is not mature, or in adults who are having pancreatic insufficiency, so the enzymes are not released, or cystic fibrosis, or so on. So the enzymes are not released from the pancreas. If the enzymes are not released, so gastric lipase will contribute will have a major contributor to the digestion or hydrolysis of lipids. So these two situations, either newborns or pancreatic insufficiency seen in adults, we're gonna see the gastric lipase act on the lipids. Okay, now, so okay, here when we ingest the akine, we'll have a lot of this fat globule. So this fat globule is composed of a lot of triglycerides, so on. Okay, so this fat, like a big fat globule, when it reaches the intestine, and because of the intestinal contractions, it will split into a lot of pieces. Okay, so it will split into a lot of pieces. See here. So suppose that this is the intestinal lumen, and we have this long big fat globule, and when it enters here, because of the intestinal contractions, it will split to small, this is not small, wait. Okay, so it will split into like small triglycerides or fat, I can say, yeah, small triglycerides, and these small, as in these guys, okay, and these should be solubilized, okay, in order to being absorbed. Okay, so those small, without the effect of the bile salts and lecithin, will not be absorbed by the intestines. Okay, I will read. Wait, I'll try to explain this in another way. So we have those bile salts and lecithin, or bile salts mainly, that is released by the bile. Okay, whenever there is, as you guys remember this picture. Okay, so whenever there is the lipid is present over here, the lipid product, there will be cholecystokinin, or present in I don't know where. The cholecystokinin will be active, and as cholecystokinin will be active, it will activate the bile. Okay, it will activate the bile to release the gallbladder to release the bile, to contract and release the bile. And as the bile is released to the intestine, as the bile released to the intestine, it has these bile salts. Okay, and these bile salts has two important functions, which is emulsification and solubilization. Emulsification and solubilization of this small droplets. So these small droplets will be emulsified and solubilized by the bile salts. And I will say how the emulsification happens. So, okay, think of it like this. So this is a small droplet. This will come the bile salt and the lecithin, and will act on this droplet. This is the bile salt and the lecithin. Okay, the bile salt and lecithin has a hydrophilic region and hydrophobic region, and the hydrophobic region is obviously acting with the interior side of this droplet, or emulsified droplets acting on the interior side, and the hydrophilic region is acting to the has a like interacting with the outside extracellular or outside environment. Sorry, outside environment. Okay, so that's for hydrophobic region and hydrophilic region, and its major function is to emulsify, solubilize, and prevent those small droplets from being what? From being like merging with each other. Because if it merged with each other, the lipases will not have an effective function in hydrolyzing those lipids. Okay. Fine. So this is the okay. So this is the emulsified. This is the emulsified droplets. This is the small droplet which has a triglyceride. Suppose it has only one triglyceride. Let's see here. So again, these are a lot of like globules which will be broken down to smaller units, and these smaller units have, for example, here triglyceride. And here, what our star pancreatic lipase will come and act. So pancreatic lipase will come and act here. In order for pancreatic lipase to act, it should have a coenzyme or cofactor which is called a colipase. So colipase is important for the effective activity of the pancreatic lipase. Okay. So yeah, and again, lipase is not a proenzyme. The proenzyme is the colipase. The colipase is a proenzyme, which is a it was a procolipase. Then it will be activated by trypsin to be colipase. Colipase is important for the lipase activity, for the what's it called, the hydrolysis of the lipid, those small lipid droplets. Okay, so the function, it will reduce the pH, and it will anchor the lipase to the lipid droplet. Now we have a triglyceride here, and the pancreatic lipase is coming up. Okay, it will act on the this droplet. What will the pancreatic lipase do? It will simply cleave the triglyceride in two locations. Okay, in two locations. You know, guys, that the triglyceride is one glycerol plus three fatty acids. So two locations of fatty acids will be cleaved, okay, by the action of pancreatic lipase. So that the end product will have a monoglyceride. Monoglyceride simply means that one glycerol plus one fatty acid. So a monoglyceride here. So I think this is the glycerol. So a monoglyceride. Okay, so this is a glycerol, and this is the fatty acid, which is bind to the glycerol, and we have here two free fatty acids, and those free fatty acids that are cleaved by the action of pancreatic lipase. Okay, so monoglyceride, the product will be monoglyceride plus two free fatty acids. Monoglyceride plus two free fatty acids. What monoglyceride is? It is simply one glycerol plus one fatty acid bind to this glycerol, and what are the free fatty acids? Is the fatty acids that are cleaved by the action of the pancreatic lipase. Okay. Okay. But let's go back. I want to emphasize on one point, is that we are doing this, all of this here, the emulsification, okay, in order to the lipase to act on the lipid and break it down. So that's why we are emulsifying those droplets. Okay, we're increasing the surface area for the lipase to act on this, what's it called, on this small droplet, and so that's the major important point behind the formation of this, what's it called, emulsified droplet. Okay, so we want the lipase to act on the those fat droplets and breaking it down to smaller subunits in order to be absorbed by the enterocytes. Remember, guys, that all of this is happening in where? In the lumen. Okay. So now, after this is a triglyceride, the emulsified one, the emulsified lipid droplet. We get the lipase comes and break it down into fatty acids, monoglycerides. Good. Okay. Fatty acids and monoglycerides will be released from here and go to the lumen of the intestine. Bile acids will come again, or bile salts will come again, and will form something which is called micelles. So first of all, we have emulsified lipid droplet, which harbors the triglycerides. Then we have micelles, which harbors the fatty acids and monoglycerides. So again, here the triglyceride broken down into fatty acids, monoglycerides. Fatty acids and monoglycerides will be incorporated into micelles, and these micelles, micelles is basically bile salt, okay, that harbors fatty acids and bile salt plus lecithin that harbor fatty acids and monoglycerides in this context, or it might harbor. We might have only like single micelle or micelle, or we want to have a mixed micelle. Mixed micelle simply means that we have fatty acids, monoglycerides, cholesterol, vitamins, so on. So mixed have a lot of components inside the micelle. Okay, so micelle is very important. Why? Because it will transform those fatty acids or those hydrolyzed lipids to the enterocytes. So it will throw them to the enterocytes, which are the cells that are lining the intestines. I hope that makes sense. Okay. Here they are illustrating what is if we have a bile salt, okay, the presence of the bile salts, and in the absence of bile salts, what will happen? So in the presence of bile salts, we have those different micelles, as I guys mentioned slide earlier. We have those mixed micelles. Mixed micelles harbor a lot of fatty acids, monoglycerides, cholesterol, so on. So it's highly concentrated with fatty acids, okay? And it will be, and in this form, which are the micelles, this one, okay, this one, okay, in this form. So in this form, the fatty acids will be absorbed by the intestines. Easy? Okay. What about if we don't have fatty acids? It means that we don't have micelles. It means that, okay, some of the fatty acids might be lipid soluble, so they will, remember guys that fatty acids, or only one fatty acid, if we have only one fatty acid, it is lipid soluble. It can enter the enterocytes. But if we compare only like suppose that this is one fatty acid, one fatty acid, they are entering here the enterocytes. If we compare this to here, where mixed micelles, we have a lot of fatty acids concentrated in the micelle. If we compare the number of fatty acids here to the number of fatty acids here, we will recognize that here we have a lot of fatty acids that are entering the enterocytes easily. Okay, I think that I've mistaken this diagram, that these are, guys, not fatty acids, not the micelles. These are emulsified droplets, and these are the micelles. Okay, these are the micelles. Okay, which will not change in the explanation, by the way. Yeah, so we have here, if we compare them, mixed micelles have a lot of fatty acids entering into the enterocyte. I hope that makes sense. Yeah. But long chain, remember that long chain fatty acids, they are not soluble. So long chain fatty acids, we should emulsify them, solubilize them, then incorporate them into mixed micelles in order for them to enter into the what's it called, into the enterocytes. Okay, so yeah, so for micelles, solubilize long chain fatty acids and will shuttle them to the enterocytes. Medium chain, as I said, guys, short chain, medium chain fatty acids might enter they are lipids, so they are water soluble. They might enter the micelles and enter the enterocytes they might enter the enterocytes without the incorporation of micelles. What about the if there is absence of bile salts? As you guys know, If there is absence of bile salts, it means that there is less fatty absorption, and as there is less fat absorption, it means that the lipids is present where the lipids are present in the intestines, and they will go into the large intestine, then will go and incorporate into the stool, forming this condition, which is steatorrhea. Steatorrhea, it simply means fat in the stool, and I think you guys discussed this in another lectures. Okay. Okay. Now, so here are this slide's supposed to be over here. Yeah, here. Or yeah, here. So this slide's supposed to be here because this is happening before incorporating into measles. This is happening in this, which is the emulsified droplets. So the pancreatic lipases, it acts on the emulsified droplets, leading to monoglyceride plus free fatty acid. The cholesterol esterases are acting on the cholesterol esters to yield cholesterol, and the phospholipase A2 is acting on lecithin, which is another component of lipids, leading to lysolecithin. Okay, and as you guys remember here, I've mentioned that we might have mixed measles. Mixed measles, I said that it simply means fatty acids, fatty acids, monoglyceride, cholesterol, like here, cholesterol, lysolecithin, or vitamins as well, which the lipid-soluble vitamins should incorporate into measles, and so on. Okay, so that's what mixed measles is, and this cholesterol esterase, phospholipase A2, they are like they are here in the to degrade cholesterol ester or lecithin. For triglycerides, we have lipase. For cholesterol ester, we have cholesterol esterase, and for lecithin, we have phospholipase A2. Okay. Okay. Now, what about if the bile salts, the mixed measles, enters the enterocytes? What will happen inside the enterocytes? So inside the enterocytes, so here is the measles. Here are the measles. We are in this here. We are here, guys. Okay, we are here. So measles will enter now the cell. We want to see what will happen after that in the cell. So it will enter to the enterocytes by measles. Those, which is the measles, enter the enterocytes. Okay. There will be the process of what's it called, reesterification, okay, or resynthesis, which simply means that here for triglycerides, we took fatty acids from them, and we form monoglycerides. Cholesterol ester, the same. We form cholesterol. We took fatty acids and form cholesterol. Again, lecithin, we took fatty acids and we form lysolecithin. Here, those fatty acids that are present in the measles will combine with each of these lipid components, leading to the reesterification and the formation of the primary product here. Okay, the primary product. So there will be reesterification happening over here, and this reesterification is happening in the smooth endoplasmic reticulum. So in the smooth endoplasmic reticulum, we'll have reesterification, yielding cholesterol esters again, triglycerides, and phospholipases, phospholipids, or lecithin, for example. Okay, so lecithin is a phospholipid, just to make sure that you understand this. Okay, and after that, those reesterified products will go to the rough endoplasmic reticulum, and in the rough endoplasmic reticulum will form something which is called chylomicron. So chylomicron will be formed in the rough endoplasmic reticulum, and chylomicron components are phospholipids from the outside. We have cholesterol ester inside, triglycerides, and we have this ApoB protein, which is important in order for chylomicrons to exit the enterocytes. So ApoB is very important in order for the chylomicrons to enter the enterocytes. And they will exit, to exit the enterocytes, and they will exit by exocytosis to the portal blood. Let's repeat it again. So we have this measles, those lipids will enter, then will be re-esterification happening in the smooth endoplasmic reticulum, which simply we are combining fatty acids again, re-esterified, combining them with the lipid components such as cholesterol, forming cholesterol ester, forming triglycerides or phospholipids, leading to now this happens in the smooth endoplasmic reticulum. This will go to the rough endoplasmic reticulum and will form the chylomicron, and this chylomicron is important in order for those component of lipids to circulate in the blood, because here they are going where? To the blood. Okay, so they are going here to the blood, and in order for chylomicrons to exit the blood, it should be there should be this ApoB protein. It's like a target. ApoB lipoprotein, it's like a target for this chylomicron to exit the enterocyte. Easy? I hope so. So we have, so the lipids can be formed in the form of emulsified droplets, mixed measles, and chylomicrons. Okay, chylomicrons to exocytose from enterocytes. So chylomicrons from the enterocytes, we have mixed measles in order for them to enter the enterocytes, and lipid droplets, emulsified droplets, in order for those lipids to be hydrolyzed by pancreatic lipases or cholesterol esterase or phospholipase A2. Okay, so that's it for the lipids part. That's it for the lipids part. We have another components of the lipids which are here. The vitamins. Vitamins are very important because it carries out a lot of like reactions in our body. We have two types of vitamins: the water soluble vitamins and the lipid soluble vitamins. Lipid soluble vitamins, these vitamins that can enter the enterocytes, but it should be incorporated into measles to do so. So they are incorporated into measles to enter the enterocytes, and they will form chylomicrons. What about the water soluble? Of course, lipid soluble are vitamin D, vitamin E, vitamin A, and vitamin K. So K, A, and E, and D, which require bile salts, they will be incorporated into measles. They should be incorporated into measles to enter the enterocytes. What about the water-soluble vitamins? We have the vitamin C. In order for vitamin C, it's a water-soluble, so it does not have to be incorporated into measles to enter the enterocyte. How does it enter the enterocytes? It enters the enterocytes by the action of sodium. It's co-transported with sodium. Here's another one which is co-transported with sodium. Let's repeat them. We have the sodium glucose co-transporter. We have short-chain fatty acid sodium co-transporter, and we have I forgot it. We have one else. Yeah, it's the amino acid sodium co-transporter, and the last one is here, the vitamin C sodium co-transporter, and this is the name of the co-transporter, which is SVCT. Okay, SVCT, which is remember, guys, that there is V and C, which is vitamin C, and sodium. So both sodium vitamin C transporter 1. Okay, so that's it for vitamin C. So for vitamin C to enter by this co-transporter, and then it will enter to the blood. Guys, this is very important. I've seen some of the SAQs asking about mention two, for example, lipid-soluble substances and one water or two water-soluble substances. Okay, so this I've seen these questions in SAQs, so make sure to know what are lipid-soluble and what are water-soluble substances. Okay, we've talked about vitamin C. Now, vitamin B12. Vitamin B12, as you guys know, you know that it is it should be combined to the intrinsic factor. Intrinsic factor is released by the, I think, the parietal cells of the stomach. Okay, so let's see here this diagram. We have from top here vitamin B12, okay, taken up by the diet, for example, and it will bind to this from the salivary gland. Once it reaches the, so wait. Okay, again, so this is the vitamin B12. It will bind to this, which is hepatocorrin, released by the salivary glands. So we have now vitamin B12 hepatocorrin complex. It will reach here the stomach, and as it reaches the stomach, it will dissociate by the action of what? By the action of by the action of the acid that's here, because here we have decrease in pH in the stomach because of the acids there. So there will be dissociation of hepatocorrin from the okay, again, so we have here vitamin B12. Okay, so we have here vitamin B12. For vitamin B12, we're gonna see this diagram, and as you guys know, that vitamin B12 has a it should be binds to intrinsic factor, and as it binds to intrinsic factor, it will be absorbed by the intestine. So vitamin B12 cannot be absorbed individually. It should bind to intrinsic factor. Okay, so let's see this diagram from top here. We have vitamin B12, okay, which will bind to this, which is released from the vitamin B12 will bind to this is a dietary one, okay, will bind to this. I don't know what's this exactly, but it will, this complex, which is vitamin B12 with a dietary protein, will be dissociated. Okay, it will dissociate in the stomach because of the increased acidity of the stomach. And as they are dissociated, vitamin B12 will going to bind hepatocorrin. Okay, so it's going to bind hepatocorrin, which is released from the salivary glands. So from the salivary glands, hepatocorrin will, with the vitamin B12, will enter, but hepatocorrin, vitamin B12 will bind in the stomach. Now, once hepatocorrin, vitamin B12 reaches the intestines, there will be dissociation of this complex by the action of the proteases, okay, or by the enzymes in the duodenum. And as there is dissociation, the duodenum, as there is dissociation, the intrinsic factor now, which is secreted over here by the parietal cells, will bind the B12 here in the I think it's the distal portion or the jejunum in the small intestine, and as B12 binds intrinsic factor, it will reach the ileum, and as it reaches the ileum, there's a specific transporter for vitamin B12, what's it called, intrinsic factor complex, to be absorbed in the ileum. So, okay, wait. Okay, yeah, sorry. So there's a specific transporter, and it will go to the lysosome. There will be further degradation of this intrinsic factor, vitamin B12, in the lysosome, and vitamin B12 then will go to the blood. This is the blood, okay. Once it goes to the blood, it will binds to transcobalamin. So let's repeat this. So dietary protein, vitamin B12 will enter the body. Once it reaches the stomach, there will be dissociation because of the acidity. Now, after this dissociation, the hepatocorrin, which is released by salivary glands, will bind B12. B12 then will go where? B12 will go to the intestine, and because of the effect of the enzymes of the intestines, of the enzyme that are released by the pancreas, there will be dissociation of the hepatocorrin from the vitamin B12. Vitamin B12 then will bind to intrinsic factor. And as it binds to intrinsic factor, it will be taken up by the distal ileum, I think. Yeah, by the distal ileum. It's not. I said that it's transporter. It's not a transporter. It's basically endocytosis, and by endocytosis, it will be incorporated into lysosome, and this lysosome, because of the enzymes present inside the lysosome, there will be dissociation of B12 from intrinsic factor, and B12 will be released to outside the cell and binds the transcobalamin, which is present where? In the blood. So transcobalamin in the blood, hepatocorrin dissociate in the stomach, dietary protein in the stomach, hepatocorrin dissociate where? In the intestines, and intrinsic factor will dissociate in the lysosome. Okay. So that's it for vitamin B12. What about vitamin B9? Now, vitamin B9, I don't know if this is important for you, but we have this form, which is pteroyl polyglutamate 7, which is, I think it's a form of vitamin B9, okay? It should be by the action of folate hydroxylase that we can find it in the enterocyte, in the brush border of the enterocyte. Folate hydroxylase will transform this from 7 into 1. And this is the absorbable form of vitamin B9. So vitamin B9, when it will be a monoglutamate, which is 1 here, polyglutamate, which is a monoglutamate 1, will be absorbed by PCFT, and this happens by the driving force is a sodium hydrogen exchanger. So because of the sodium over here, sodium will be recycled, and the pteroyl monoglutamate will enter the enterocyte, and that's it for vitamin B9. So vitamin B9, in order to be absorbed, it should be a monoglutamate, and it will be this happens by the folate hydroxylase. And how does it enter the cell? It will enter by the PC. It will enter by PCFT, which is important for vitamin B9. Okay. To be absorbed, I mean. Okay, so that's the last slide in this lecture. We have some clinical correlations, such as vitamin B12 deficiency and vitamin B9 deficiency. What will happen if there is vitamin B12 deficiency? Or where can we see vitamin B12 deficiency? It's basically when there is deficiency in intrinsic factor, in autoimmune disorders, or in the context of gastrectomy. Whenever there is resection of the stomach, it means that there is no parietal cells, and intrinsic factors will not bind to vitamin B12. So if vitamin B12 is not there, deficient, this will lead to a type of anemia, which is called pernicious anemia. Okay, pernicious anemia, where we'll have the RBCs are not well developed. RBCs are not well developed. And please note, guys, that both of these, so we'll have before that we have the pernicious anemia, and this where we can see in megaloblastic, the cells will have like a megaloblastic anemia, and this is what a megaloblastic anemia. Megaloblastic anemia, it simply means that the cells are bigger in size, okay? And anemia means that there is fewer RBCs. Okay. These two conditions, B12 and B9, can affect RBCs. Okay, can affect RBCs. Note this. I want you to note this. Okay. What about if there is vitamin B9 deficiency? If there is vitamin B9 deficiency, there is it means that there is no folate, and if there is no folate, the DNA synthesis is affected. Okay, so this is very important. If there is a pregnant woman not taking folate supplements, and if this happens, the baby will have might have some abnormalities, such as neural tube defects. And I think you guys took this in foundation, what a neural tube defect is. So the baby will have this sort of abnormalities, and that basically happening because the B9 vitamin B9 is deficient in our body, and this is very dangerous and the pregnant woman. Okay. So vitamin B12, pernicious anemia, megaloblastic anemia, so on, and vitamin B9 neural tube defects, and both of these will affect the RBCs, and vitamin B9 will affect DNA synthesis. Okay, and that's the last slide for the lecture. These 3 slides, I think, it's like a review for the lecture. I will let you keep you guys go over it on your own. Please, if you have any question, don't hesitate to contact me. I hope that I explained this lecture well, and I hope you guys benefit from this. And yeah, that's my contact information over here. Okay, so that's it for this